the mystery of our origins. In the vast theater of the universe, where billions of galaxies swirl in endless spirals and countless stars ignite with furious brilliance, there exists one small, blue planet that holds the unique distinction of being our home, Earth. Its story is not just the story of rocks, gases, and cosmic dust coming together by chance. It is also the story of us, the observers who now seek to understand the mysteries of our own beginnings. To ask how Earth was formed is to ask a question that sits at the very root of human curiosity. It is a question that bridges the boundary between science and wonder, between the cold mechanics of cosmic physics and the warmth of life that now flourishes on its surface. The journey of Earth's birth is not a simple tale, but a vast epic that stretches across billions of years, across epochs of chaos, violence, creation, and transformation. When we gaze up at the night sky and see the endless scattering of stars, it is easy to feel small and insignificant. Yet, hidden in those stars lies the key to understanding our planet's origins. Earth was not born in isolation, but out of a cosmic family, the solar system. To unravel how Earth formed, we must trace back to a time before there were planets, before the sun itself burned bright in the heavens. We must journey back to a cosmic cradle where immense clouds of gas and dust floated aimlessly in space, remnants of older stars that had lived and died, scattering their elements into the cosmos. It was from this interstellar material, enriched by generations of stellar life and death, that our sun and its planets, including Earth, were destined to emerge. The Earth as we know it today, with oceans covering 70% of its surface, continents drifting across tectonic plates, and life thriving in diverse forms, is the result of nearly 5 billion years of cosmic history. This span of time is so vast that human imagination struggles to fully comprehend it. Civilizations rise and fall in mere thousands of years, yet the Earth's story is written in billions. To tell this story is to dive into deep time, into a scale where mountains rise and crumble into dust, oceans form and evaporate, and entire species come and vanish, all in what amounts to only brief moments in Earth's vast life. The very atoms that make up our bodies today, carbon, oxygen, nitrogen, iron, were forged long before Earth existed, in the fiery furnaces of ancient stars. These stars lived brilliant but brief lives, exploding in catastrophic supernovae that scattered their elements across the cosmos. When we say we are made of star stuff, we mean it literally. Earth's creation, therefore, is not an isolated event, but the latest chapter in the cosmic cycle of birth, death, and rebirth. Our planet is a child of the stars, and its history is inseparably linked to the wider history of the universe. But Earth's formation is also a story of violence and chance. It did not appear gently or peacefully, but through a chaotic dance of collisions, explosions, and transformations. Imagine a young solar system, a swirling disk of dust and gas circling around the newborn sun. Within this turbulent disk, small grains of dust clumped together under the invisible force of gravity, colliding again and again, growing into larger bodies called planetesimals. These planetesimals, in turn, smashed into one another, merging in fiery impacts to form larger protoplanets. It was within this violent nursery that Earth began to take shape, growing from a small rocky embryo into a world large enough to hold on to an atmosphere and water, and eventually stable enough to support life. The Earth that we inhabit today bears little resemblance to the early planet that first emerged in the chaos of a young solar system. At the beginning, Earth was a molten sphere, its surface constantly reshaped by meteoric bombardments, its interior seething with heat from radioactive decay and constant impacts. It was not a hospitable place for life, nor did it resemble the blue and green paradise we see from space today. The early Earth was unstable, hostile, and constantly changing. Yet, over time, through processes that stretched across hundreds of millions of years, it cooled, solidified, and slowly evolved into the world that could nurture oceans, continents, and eventually living creatures. Why is the story of Earth's formation so important to us? Because it reminds us that we are part of something greater than ourselves. Our existence is not random but a continuation of cosmic processes that have been unfolding since the dawn of time. Understanding Earth's origin is not simply an exercise in science. It is also a way of finding our place in the universe. It connects us to the stars, to the galaxies, and to the unfathomable immensity of the cosmos. It allows us to see our home, not just as a planet, but as a miracle born out of chaos. As we embark on this exploration of how Earth was formed, we must be prepared to journey across scales of time and space that stretch beyond ordinary human comprehension. We will begin with the birth of the sun, the central force around which everything else revolves. We will witness the swirling nebula that gave rise to our solar system, the process of accretion that built up the planets, and the violent collisions that defined the young Earth. We will examine the formation of the moon, born out of a cataclysmic impact that forever altered Earth's destiny. We will trace the slow cooling of the planet, the rise of oceans and continents, and the gradual emergence of an environment capable of sustaining life. This is not merely a story of geology or astronomy. It is a story of creation on a cosmic scale. It is the story of how a chaotic cloud of gas and dust was transformed into a living world, a world that, billions of years later, would give birth to beings capable of reflecting on their own origins. The story of Earth's formation is, ultimately, the story of us. It is a reminder that in the midst of the universe's vast indifference, life has found a way to exist and flourish. And so, with curiosity as our guide and science as our map, we set forth on a journey back in time, back to the beginning, before there was land or sea, before there was air to breathe or life to thrive, back to the moment when a faint glimmer of possibility sparked in a cloud of cosmic dust. This is the story of how Earth was formed, and it begins not on the surface of our planet but in the depths of space, where stars are born and worlds are made. To understand how Earth was formed, we must first step back even further in time and explore the dramatic events that shaped the solar system itself. Earth did not appear in isolation. It emerged as one world among many in a family of planets, all born from the same colossal cloud of dust and gas that once drifted through the Milky Way. The stage for Earth's birth was set by one of the most important processes in the universe, the birth of a star. Our sun, the center of the solar system and the engine of all life on Earth, had to exist first before Earth could ever begin to form. Around 4.6 billion years ago, a massive interstellar cloud floated through the arm of our galaxy. This cloud, known as a solar nebula, was not uniform. It was a patchy mix of hydrogen, helium, and heavier elements like carbon, silicon, oxygen, and iron, materials that had been scattered across space by countless dying stars. This nebula was immense, stretching across light years, and for a long time, it simply drifted in the dark void, waiting for the right trigger to collapse in upon itself. That trigger was likely a powerful external shockwave, perhaps from a nearby supernova, a massive star that had reached the end of its life and exploded in a cataclysm of unimaginable force. The shockwave disturbed the balance of the nebula, compressing its gases and setting into motion the chain of events that would eventually lead to the formation of the sun, the planets, and Earth itself. As gravity began to pull the gas and dust inward, the nebula started to collapse. But this collapse was not uniform. As the material fell inward, it also began to rotate. Conservation of angular momentum caused the nebula to spin faster and faster, flattening it into a giant rotating disk. At the center of this spinning disk, matter accumulated, growing denser and hotter as gravity pulled more and more material inward. This was the beginning of our sun, a protostar, a young star in the making. The temperature at the heart of this growing protostar rose to millions of degrees. At a critical point, hydrogen atoms began to fuse into helium in nuclear reactions, releasing enormous amounts of energy. The sun had been born. Its ignition illuminated the surrounding disk and sent out powerful solar winds that began to push lighter gases outward, shaping the structure of the entire solar system. But while the sun blazed into existence at the center, the story of Earth's creation was just beginning in the swirling disk of gas and dust that circled it. This disk, known as the protoplanetary disk, was the nursery of planets. It contained all the raw materials that would eventually form the rocky inner planets, Mercury, Venus, Earth, and Mars, as well as the giant gas planets further out. In this disk, tiny grains of dust and ice particles began to stick together, held first by weak electrostatic forces and later by gravity as they grew larger. These small clumps grew into kilometer-sized objects called planetesimals. The solar system at this stage was a chaotic place, filled with millions of these planetesimals crashing into each other. Some shattered into fragments, while others merged, growing larger with every collision. This process of growth by collision and merging is known as accretion, and it was the fundamental mechanism by which Earth and the other planets began to take shape. Closer to the Sun, where heat was intense, only metals and rocky materials could survive. Lighter substances like water, methane, and ammonia evaporated or were pushed further out by the solar wind. This is why the inner planets, including Earth, are rocky and dense, while the outer planets are gas-rich giants. Earth's destiny as a rocky world was determined at this very early stage by its position in the solar system. As planetesimals continued to collide and merge, they formed larger bodies, known as protoplanets. These were planetary embryos, small planets in the making. Some of them were destroyed in catastrophic collisions, while others survived, growing ever larger. Among these protoplanets was the early Earth, still molten, unstable, and vulnerable to violent impacts. The young solar system was far from peaceful. Gigantic collisions were frequent, reshaping the surfaces of growing worlds and altering their orbits. Some planetesimals were flung out of the solar system entirely, while others crashed into the sun. Still others became moons or were captured as asteroids. It was in this cosmic battlefield that Earth steadily gained mass, becoming one of the dominant protoplanets in its orbital zone. At the same time, the larger outer planets, Jupiter, Saturn, Uranus, and Neptune, were forming. Their immense gravity influenced the orbits of countless planetesimals, sending some inward to bombard the inner planets, including Earth. These bombardments delivered additional material to Earth, contributing not only to its growth but also to its eventual inventory of elements, including some of the water and volatiles that would later play crucial roles in shaping Earth's atmosphere and oceans. The solar system gradually began to organize itself into the structure we recognize today, with the sun blazing at the center, rocky planets orbiting close by, and giant planets dominating the outer regions. But this process took tens of millions of years, and during that time, Earth continued to grow, suffer impacts, and evolve. The birth of the solar system is not just a backdrop to Earth's story, it is the essential foundation. Without the collapse of the solar nebula, there would be no sun, no planets, and no Earth. Without the violent collisions of planetesimals, there would be no rocky surface upon which continents could rise. And without the unique placement of Earth within the solar system, not too close to the sun, not too far, we would not have the conditions necessary for liquid water and life. This delicate balance, shaped by cosmic processes billions of years ago, is what makes Earth unique. While there are countless planets across the universe, Earth occupies a position in space and a history of formation that made it habitable. It is often called the Goldilocks planet because it sits in just the right spot in the solar system for life as we know it to exist. The foundation for that uniqueness was laid during the turbulent birth of the solar system, when swirling dust and gas gave rise to the sun and the planets. Thus, before we can dive into the details of how Earth itself took shape, we must appreciate the cosmic stage on which it was born. The solar system's birth was a story of collapse, ignition, and accretion, a story of chaos slowly settling into order. Out of this chaos emerged our sun, blazing with energy, and around it circled the seeds of planets, waiting to grow into worlds. Among them was the tiny rocky embryo that would one day become Earth, a planet destined to harbor life and to become the stage for humanity's quest to understand the universe itself. The early solar system, though it may appear orderly to us today, was once a turbulent and violent place. After the sun ignited at its center and began blazing with light, the swirling protoplanetary disk that surrounded it became a cosmic construction site. Within this disk, dust grains, ice particles, and fragments of rock collided, stuck together, and slowly grew into larger and larger bodies. This process, known as accretion, is one of the most important chapters in Earth's formation. It was through accretion that our planet emerged from the chaos of countless smaller pieces, eventually becoming the massive and stable world we inhabit today. To understand accretion, imagine a vast cloud of tiny particles orbiting the sun. These particles were made of silicates, metals, and ices, remnants of earlier stars and the raw materials of planets. At first, their collisions were gentle, and static electricity allowed microscopic grains to stick together, forming clumps only a few millimeters across. Over time, these clumps grew larger, forming pebbles, rocks, and boulders. As they gained mass, gravity began to play a role. Gravity is a weak force at very small scales, but once objects grow to a certain size, it becomes the dominant factor, pulling more material inward and accelerating growth. Within a few million years, these growing bodies, called planetesimals, became kilometers across. They were the seeds of planets, scattered throughout the disk like countless embryonic worlds. Each planetesimal had its own gravitational field, however small, and they began to interact with one another. Some merged in relatively gentle collisions, while others were shattered in catastrophic impacts. This period of cosmic growth was not peaceful but chaotic, with countless collisions reshaping the young solar system every moment. As planetesimals grew, a process known as gravitational focusing amplified their ability to attract additional material. Larger bodies pulled smaller ones toward them, increasing the likelihood of collisions and growth. This created a runaway effect. The bigger a planetesimal became, the faster it grew. Eventually, some planetesimals reached hundreds of kilometers in diameter. These were no longer mere space rocks. They were protoplanets, planetary embryos with enough gravity to dominate their immediate neighborhoods. The early Earth was one of these protoplanets. It began as a small rocky seed, perhaps no larger than a few tens of kilometers across, and gradually grew as it swept up surrounding debris. Over millions of years, it grew larger and larger, reaching the size of Mars before continuing its journey toward becoming a full-fledged planet. But Earth was not alone. In its orbital region, other protoplanets also grew, competing for material and colliding with one another. Only the strongest would survive. The collisions that drove accretion were not always gentle. When two large planetesimals collided at high speed, the result could be catastrophic, releasing energy equivalent to billions of nuclear bombs. Some impacts shattered bodies into fragments that later reassembled, while others fused two worlds together in fiery union. Each impact released immense heat, contributing to the molten state of the early Earth. At times, the entire surface of the growing Earth may have been a global ocean of magma, its crust unable to solidify under the constant bombardment of material from space. This period of violent accretion was also critical in shaping the composition of Earth. As planetesimals collided and merged, their interiors differentiated. Denser materials like iron and nickel sank toward their centers, while lighter silicates floated to the surface. When these bodies merged with Earth, their metals sank into its growing core, while lighter materials contributed to its mantle and crust. In this way, Earth developed its layered internal structure, with a dense metallic core surrounded by a rocky mantle and a thin crust. The outer regions of the solar system experienced a different process. Far from the sun, where temperatures were lower, ices and gases could survive, and planetesimals grew into gas giants like Jupiter and Saturn. These massive worlds exerted tremendous gravitational influence, shaping the orbits of countless smaller bodies. Many planetesimals were flung into the inner solar system, where they bombarded Earth and the other rocky planets, adding to their mass and altering their compositions. Some scientists believe that much of Earth's water may have been delivered during this time by icy planetesimals and comets, a gift from the outer solar system that would one day make life possible. As Earth grew, its increasing gravity allowed it to sweep up more and more material. Yet growth was not unlimited. In the region around Earth's orbit, only a finite amount of material was available. Once the local reservoir of planetesimals was consumed or ejected, Earth's growth slowed. By around 50 to 100 million years after the birth of the Sun, Earth had reached nearly its full size. It was no longer just a planetesimal or a protoplanet. It was becoming a true planet, massive enough to hold on to an atmosphere and maintain geological activity within its core. Still, Earth's journey was far from complete. The final stages of accretion were marked by fewer but more dramatic collisions. One of these collisions, occurring about 4.5 billion years ago, would forever change Earth's destiny. A Mars-sized protoplanet, often called Theia, is believed to have smashed into the young Earth in a titanic impact. The energy released by this collision was so immense that much of Earth's outer layer was blasted into space. Some of this material eventually coalesced to form the Moon, Earth's faithful companion. This event not only reshaped Earth's surface, but also stabilized its tilt, giving rise to the predictable seasons that have shaped the rhythm of life for billions of years. The process of accretion reveals an important truth about Earth's formation. Our planet is not a product of calm, orderly growth, but of relentless chaos. It is the survivor of billions of collisions, each one adding to its mass, altering its composition, and reshaping its destiny. Without accretion, Earth would not exist. Without the countless planetesimals that merged into its growing body, there would be no continents, no oceans, and no life. By the end of the accretionary period, Earth was a young, molten world, its surface battered and unstable, its atmosphere thick with volcanic gases, and its interior still roiling with heat from radioactive decay and constant impacts. Yet within this chaos lay the seeds of stability. The Earth had grown massive enough to establish a strong gravitational hold, keeping its atmosphere in place and allowing water to remain on its surface. The foundations for a habitable planet had been laid, even though Earth itself was still far from hospitable. The rise of planetesimals and the process of accretion remind us of the incredible power of small beginnings. From tiny grains of dust, through countless collisions and mergers, emerged a planet capable of hosting oceans, continents, and eventually life itself. Earth's story, like the story of life, begins with the smallest pieces coming together to form something greater than the sum of its parts. The stage was now set for the next dramatic chapter, the transformation of a violent, molten protoplanet into a world with a stable crust, a dynamic interior, and a companion moon that would guide its rhythms. The chaos of accretion had built the foundation, but the Earth we recognize today was still waiting to emerge from fire, impact, and transformation. By the time Earth had grown into a massive protoplanet, the solar system was still very young and chaotic. Billions of planetesimals had already merged or been destroyed, but the inner solar system remained crowded with planetary embryos, worlds in the making. These protoplanets, some as large as Mars, orbited the Sun in unstable paths, colliding and reshaping one another. Among these restless worlds was the young Earth, already close to its present size, but still molten, unstable, and battered by frequent impacts. Yet one collision would change everything, the giant impact event that gave birth to the Moon and altered Earth's destiny forever. The Earth at this stage, about 4.5 billion years ago, was not the calm blue planet we know today. Its surface was dominated by vast oceans of magma, the result of intense heat from radioactive decay, constant bombardment by asteroids, and the gravitational energy of its own formation. Volcanoes belched gases into a thick, toxic atmosphere of carbon dioxide, nitrogen, water vapor, and sulfur compounds. The planet spun faster than it does today, completing a rotation in as little as 6 hours. Day and night passed in the blink of an eye. Into this violent and unstable world came a cosmic intruder, a protoplanet now called Theia. Theia was a Mars-sized body, perhaps slightly smaller than Earth, that had formed in a nearby orbit around the Sun. For millions of years, it followed a path that brought it dangerously close to Earth. Gravitational interactions with other protoplanets, and especially the immense influence of Jupiter, destabilized its orbit until, at last, it crossed Earth's path. What followed was one of the most catastrophic and transformative events in planetary history, a collision so immense that it reshaped Earth itself. When Theia struck Earth, the impact released energy beyond imagination. Scientists estimate it was equivalent to tens of millions of nuclear bombs exploding at once. Theia did not simply bounce off Earth, it merged with it. Much of Theia's core and mantle sank into Earth's own interior, adding to the planet's mass and further heating its already molten state. At the same time, huge amounts of Earth's outer layers were blasted into space. For a brief moment, Earth may have had a system of glowing rings like Saturn, made not of ice but of molten rock and vaporized silicate material. This ejected material did not scatter into deep space. Earth's gravity held it captive, and within weeks to months, the debris began to coalesce. Through the same process of accretion that had formed the planets, these fragments of rock and vapor merged into a single body orbiting Earth. This body grew larger and larger until it became the Moon. Unlike other moons in the solar system, which were often captured asteroids or leftover planetesimals, Earth's moon was born directly from Earth itself. It is a child of our planet, forged in violence and fire. The formation of the moon had profound consequences for Earth. First, the collision fundamentally changed Earth's rotation and tilt. Before the impact, Earth's axis may have been more erratic, but afterward, it stabilized at a tilt of about 23.5 degrees. This tilt is the reason we experience seasons, as different parts of Earth receive varying amounts of sunlight during its yearly orbit around the Sun. Without the stabilizing effect of the Moon's gravitational pull, Earth's tilt could have wobbled chaotically over time, leading to extreme climate variations that might have prevented life from ever gaining a foothold. Second, the impact slowed Earth's rapid rotation. Before the collision, Earth spun so quickly that a day may have lasted only 6 hours. Afterward, as angular momentum was transferred to the Moon's orbit, Earth's day lengthened. Over billions of years, this process of tidal interaction between Earth and the Moon has continued, gradually slowing Earth's rotation to the current 24-hour cycle we know today. This steady rhythm of day and night has shaped the biological patterns of life across the planet. Third, the Moon has played a vital role in Earth's geology and tides. Its gravitational pull creates ocean tides, stirring the waters of Earth's seas and driving nutrient cycles essential for life. In the early days, when the Moon was much closer to Earth, tides were far stronger, shaping coastlines and perhaps even influencing the development of early life in tidal pools. Without the Moon, Earth would be a very different world, not just in appearance, but in its very capacity to sustain complex ecosystems. The impact also contributed to Earth's internal differentiation. The immense heat generated by Theia's collision may have melted large portions of Earth's interior, allowing heavy metals to sink deeper into the core and lighter materials to rise toward the surface. This helped establish the layered structure of Earth's interior: a dense iron-nickel core, a silicate mantle, and a thin outer crust. This structure is crucial to Earth's long-term habitability, as it powers the magnetic field that shields the planet from harmful solar radiation and drives plate tectonics that recycle nutrients and create diverse environments. Evidence for the giant impact hypothesis comes from many sources. The Moon's composition is remarkably similar to Earth's outer layers, suggesting they share a common origin. Yet the Moon has far less iron than Earth, consistent with the idea that it formed from Earth's crust and mantle rather than its core. Lunar rocks also show isotopic signatures nearly identical to those of Earth, unlike any other body in the solar system. These clues point strongly to a shared origin in a cataclysmic impact. For Earth, the giant impact was both destructive and creative. It erased whatever surface features the young planet may have had, leaving behind a molten world. But it also gave Earth a companion that has shaped its destiny ever since. The Moon's presence has been a stabilizing force for billions of years, helping Earth maintain the conditions necessary for life. It has lit up the night sky, guided the rhythms of oceans, and inspired countless myths and stories in human cultures. Yet its origin lies not in peace, but in cosmic violence, a reminder of the chaotic processes that gave birth to our world. After the impact, Earth entered a new phase of its evolution. Its surface remained molten for millions of years, a seething ocean of magma constantly reshaped by volcanic eruptions and bombardments from smaller asteroids and comets. Gradually, however, the planet began to cool. A thin crust formed over the molten interior, fragile and easily broken, but it marked the beginning of a solid surface. Volcanic activity continued to shape the young planet, releasing gases that thickened its atmosphere. Water vapor condensed into clouds, and eventually, rain began to fall, perhaps for millions of years, filling the low basins with the first oceans. Thus, out of fire and destruction emerged the building blocks of a habitable world. The giant impact was not the end of Earth, but a turning point, transforming it into a planet with a moon, a stable rotation, and the potential for oceans and life. The Earth that arose from this event was still young, hostile, and unstable, but it had crossed a threshold. It was no longer just a molten sphere of rock. It was a planet with a destiny, one that would eventually include continents, ecosystems, and intelligent beings who would one day look back and try to understand their planet's fiery origins. After the colossal collision with Theia that gave birth to the Moon, Earth was left as a seething, molten world. Its surface glowed with fiery heat, much of it still covered by vast magma oceans. The planet's interior boiled with energy from three powerful sources: the heat of radioactive decay, the gravitational energy from its own formation, and the unimaginable energy released during the giant impact. For millions of years, Earth was a hellish landscape, a place utterly inhospitable to life. Yet this fiery beginning was not permanent. Slowly, step by step, Earth began to cool, and in doing so, it laid the foundations for the solid surface, the oceans, and the atmosphere that would eventually make it habitable. The process of cooling was not simple. Even as Earth radiated heat into space, its surface was bombarded by countless asteroids and comets left over from planetary formation. Each impact released additional energy, reheating portions of the surface, and often remelting areas of the crust that had begun to solidify. This period, often called the Hadean Aeon, named after Hades, the ancient god of the underworld, was a time of relentless bombardment, volcanic eruptions, and instability. Yet amid this chaos, Earth was gradually transforming from a molten orb into a solid world. As the magma oceans cooled, the first crust began to form. This early crust was thin and fragile, constantly broken apart by impacts and volcanic activity. But its existence marked an important turning point. Earth now had a surface upon which water could eventually collect and continents could rise. The crust that formed during this time was likely basaltic, similar to the dark volcanic rock found in ocean floors today. It was heavy and dense, easily recycled back into the mantle by convection currents and impacts. This meant that Earth's earliest crust probably did not survive for long. What we see today in Earth's oldest rocks, dating back about 4.0 billion years, are the remnants of later stages of crust formation, after the planet had stabilized somewhat. While the crust was forming, Earth's atmosphere was also taking shape. The giant impact and the constant volcanic eruptions had released massive amounts of gas from Earth's interior. This process, known as outgassing, created a thick, toxic atmosphere composed primarily of carbon dioxide, nitrogen, water vapor, ammonia, and methane. There was no free oxygen in this early atmosphere. It was alien to the kind of life we know today. Still, it played a vital role in Earth's evolution. The thick blanket of gases trapped heat, slowing the cooling process, while water vapor in the atmosphere prepared the way for one of Earth's greatest transformations, the formation of the oceans. As Earth cooled further, the water vapor in the atmosphere began to condense. Clouds formed, and eventually rain began to fall. But this was no ordinary rain. It may have lasted for millions of years, a torrential downpour that filled basins and lowlands with liquid water. This was the birth of Earth's oceans. Some of the water may also have been delivered by icy comets and water-rich asteroids bombarding Earth during this time, adding to the supply already present from volcanic outgassing. The result was the same. Earth became a planet with vast oceans, covering much of its surface, a feature that would define it as the blue planet of our solar system. The arrival of water was transformative. Oceans stabilized Earth's climate by absorbing heat and carbon dioxide, reducing extreme temperature swings. They provided a medium for chemical reactions that would eventually lead to life. And they reshaped Earth's geology, eroding rocks, transporting sediments, and creating new landscapes. From this point onward, water would be one of the most powerful forces shaping Earth's destiny. As Earth's crust thickened and cooled, the planet's interior also began to organize itself into distinct layers. The dense iron and nickel core, already formed during the earliest stages, generated a strong magnetic field through the motion of liquid iron in its outer core. This magnetic field was critical. It protected the planet's atmosphere from being stripped away by the solar wind, allowing Earth to retain its air and water. Without this shield, Earth might have suffered the same fate as Mars, which lost much of its atmosphere early in its history. Meanwhile, convection in Earth's mantle drove the earliest forms of tectonic activity. Plates of crust moved slowly across the surface, colliding, breaking, and diving back into the mantle. This tectonic motion recycled material, released gases into the atmosphere, and gradually built up the first protocontinents. These early land masses were small and scattered, nothing like the vast continents we know today, but they represented the beginnings of Earth's dynamic surface. The atmosphere during this time was thick with greenhouse gases, especially carbon dioxide. This created a powerful greenhouse effect, trapping heat and keeping Earth warm despite the fact that the sun was about 30% dimmer than it is today. Without this greenhouse effect, Earth might have frozen over entirely. Instead, the planet maintained liquid water, a key ingredient for life. However, the early atmosphere was still toxic to modern organisms. Breathing it would have been impossible for humans or animals. It would take billions of years before oxygen transformed Earth's air into something we could breathe. The interplay between cooling, crust formation, atmosphere, and water set the stage for the next chapters in Earth's history. From a molten sphere emerged a planet with a rocky surface, oceans of water, and a protective atmosphere. It was still a dangerous and unstable world, racked by volcanic eruptions and frequent asteroid impacts, but it had crossed an essential threshold. It was no longer a barren, lifeless rock, but a planet with the conditions necessary for chemistry, stability, and eventually life. During this time, the heavy bombardment of Earth continued. Asteroids and comets rained down in a period known as the Late Heavy Bombardment, about 4.1 to 3.8 billion years ago. These impacts scarred Earth's surface and may have vaporized oceans temporarily, but they also delivered valuable elements and molecules, including water and organic compounds, which enriched Earth's chemistry. Some scientists believe this bombardment may have been critical in delivering the raw ingredients for life, seeding the young planet with the building blocks of biology. Despite the violence, Earth endured. Over hundreds of millions of years, the crust thickened, the ocean stabilized, and the atmosphere evolved. Volcanic activity continued to recycle gases and shape the surface, while tectonic motion began the long process of building continents. The stage was now set for the next great transformation, the appearance of life. The story of Earth's cooling, crust formation, and early atmosphere is one of resilience and transformation. Out of fire and chaos came water, air, and land, the essential ingredients for habitability. The Earth we know today is the product of these processes, guided by the interplay of heat, gravity, chemistry, and chance. Without the cooling of magma oceans, there would be no solid ground. Without volcanic outgassing, there would be no atmosphere or water. Without oceans, there would be no stable climate. Together, these forces transformed Earth from a molten inferno into a dynamic, living world. In this way, Earth's early history reminds us that stability is born from chaos. The very violence that seemed to threaten the planet's survival, the impacts, the eruptions, the constant bombardment, was also the force that gave it oceans, continents, and an atmosphere. Earth's habitability is not the result of peace, but of transformation, a balance struck between destruction and creation. From the fiery crucible of the Hadean, a world emerged that could cradle life. And soon, in the dark depths of the oceans, the first sparks of biology would begin to flicker, setting in motion the next great chapter of Earth's story. By the time Earth had cooled enough to form a stable crust and gather its oceans, it was still a very different world than the one we know today. The air was unbreathable, the sky was hazy with volcanic gases, and the seas were dark, acidic, and churning. Yet these harsh conditions were not a curse but a foundation, a chemistry lab on a planetary scale. The interaction of atmosphere, oceans, and cosmic bombardment during these early stages shaped the very destiny of Earth, creating an environment capable of nurturing life. The early atmosphere of Earth, often called the second atmosphere, was not inherited from the solar nebula. The violent processes of planetary formation and the giant impact with Theia had stripped away any original gases Earth might have captured from the primordial solar cloud. Instead, the air we speak of was forged by the interior of the Earth itself, through outgassing. Volcanoes and fissures vented enormous amounts of steam, carbon dioxide, nitrogen, hydrogen sulfide, methane, and trace gases into the skies. This thick, heavy, toxic mixture bore little resemblance to the oxygen-rich air we breathe today. It was hot, suffocating, and laced with greenhouse gases that trapped heat, preventing Earth from freezing beneath a fainter young sun. The role of water vapor in this atmosphere was profound. As Earth cooled, the vapor condensed into liquid water and fell as endless rains, filling the low basins and forming the first oceans. These oceans may have appeared as early as 4.4 billion years ago, as suggested by tiny mineral crystals called zircons, which bear chemical fingerprints of interaction with liquid water. If true, this means Earth had oceans astonishingly early in its history, within only a few 100 million years after its violent birth. Water, once trapped in minerals deep in the mantle or delivered by asteroids and comets, now spread across the surface, transforming Earth into the blue planet we recognize today. These early oceans were not like the clear blue waters of modern Earth. They were dark and murky, infused with dissolved iron and minerals from volcanic vents. The atmosphere above them was thick with carbon dioxide, giving the seas an acidic quality. Lightning flashed across stormy skies, and frequent asteroid impacts boiled sections of the ocean into steam. Yet in these waters, bathed in energy from the sun, the heat of the Earth, and the bombardment from space, the stage was set for the origins of life. The role of cosmic bombardment during this era cannot be overstated. For hundreds of millions of years after Earth's formation, the solar system was still in disarray. Countless asteroids, planetesimals, and comets roamed the inner solar system, colliding with planets and moons in violent displays of energy. Earth was no exception. Some of these impacts were catastrophic, temporarily vaporizing oceans and sending shockwaves through the planet. Others were smaller, delivering valuable cargoes of organic molecules and water. This period, sometimes called the Late Heavy Bombardment, around 4.1 to 3.8 billion years ago, was both destructive and enriching. On one hand, massive impacts could sterilize the surface, boiling oceans into steam and making survival impossible for any nascent life. On the other, these same impacts were cosmic delivery services carrying amino acids, sugars, and other complex organic molecules, the very building blocks of life, from the depths of space. Meteorites found on Earth today contain such molecules, demonstrating that the cosmos itself is rich with the seeds of biology. The bombardment of early Earth, therefore, may have played a dual role, sometimes wiping the slate clean, and at other times sowing the seeds of potential. In this dynamic setting, Earth's oceans and atmosphere worked together as a planetary laboratory. The thick carbon dioxide, rich air created a strong greenhouse effect, which was critical because the young sun shone about 30% dimmer than it does today. Without this heat-trapping atmosphere, Earth's oceans might have frozen solid, halting the possibility of life. Instead, the greenhouse gases maintained a delicate balance, warm enough to keep water liquid, but turbulent enough to drive storms, chemical reactions, and circulation patterns. The chemistry of the oceans was equally vital. Volcanic activity released not only gases, but also minerals and metals into the seas. Hydrothermal vents along the ocean floor spewed hot, mineral-rich water, creating chemical gradients that provided energy for reactions. These vents, surrounded by towering chimneys of iron and sulfur compounds, may have been among the first havens for life on Earth. Here, in the darkness of the ocean floor, energy, water, and chemistry combined in just the right ways. The interaction between the atmosphere and oceans also began to regulate Earth's climate. Carbon dioxide, dissolved in water, formed carbonic acid, which reacted with rocks and minerals to create carbonates. This natural carbon cycle helped remove excess carbon dioxide from the air, slowly stabilizing temperatures. Although this system was primitive in its earliest form, it foreshadowed the vital planetary thermostat that continues to operate today, keeping Earth's climate relatively stable over billions of years. The magnetic field, generated by the movement of molten iron in Earth's outer core, also played an essential role during this time. By deflecting the solar wind, a constant stream of charged particles from the sun, the magnetic field prevented the early atmosphere from being stripped away. Without this invisible shield, Earth's air and water could have been lost to space, as happened on Mars, leaving the planet barren and dry. Thus, deep within Earth's core, forces were already working to ensure that its surface remained habitable. Despite its hostility, the early Earth was far from a dead planet. Its atmosphere and oceans provided stability, its bombardment supplied crucial ingredients, and its geology created diverse environments where unique chemistry could occur. What to us seems like a nightmare world, boiling seas, toxic skies, and fiery impacts, was in fact a crucible of creation. Every storm, every eruption, every collision contributed to the rich chemical soup in which life's first sparks would eventually ignite. It is also important to recognize the fragility of this balance. If Earth had been slightly smaller, it might not have held on to its atmosphere. If it had orbited slightly farther from the sun, its oceans might have frozen. If it had lacked a magnetic field, the solar wind could have stripped its gases away. The fact that all these factors aligned is not just remarkable, it is essential to why Earth is unique among the rocky planets of our solar system. Mars lost its atmosphere and became a cold desert. Venus retained a thick atmosphere, but turned into a scorching furnace. Earth alone found the balance between air, water, and temperature that made it a cradle for life. By the end of this turbulent period, Earth had settled into a new state. It had a stable crust, vast oceans, a thick but protective atmosphere, and a magnetic field shielding it from space. The heavy bombardment began to wane, allowing longer stretches of stability. The planet was no longer a molten inferno or a shattered battlefield of impacts, but a world capable of chemistry, balance, and continuity. The basic stage had been set. The curtain was ready to rise on the next act, the emergence of life itself. The story of Earth's early atmosphere, oceans, and bombardment is a tale of paradoxes. Violence created stability. Toxic gases prepared the way for breathable air. Acidic oceans paved the path for life. Catastrophic impacts may have both destroyed early attempts at biology and delivered the very molecules that would make life possible. Out of destruction came creation, and from chaos emerged order. In this way, the early Earth reveals a profound truth, that life is born not in comfort, but in challenge. The harshness of those early days was not a barrier, but the very force that shaped the destiny of our planet. With the decline of the late heavy bombardment around 3.8 billion years ago, Earth began to experience a new phase in its history, a period of relative stability. This was not stability in the sense of a quiet, peaceful world. Volcanoes still erupted, tectonic plates still shifted, and meteorites still struck, but compared to the violent chaos of earlier eons, the planet now had intervals long enough for more permanent geological and chemical systems to take shape. The stage was set for the next great transformation, the growth of continents and the appearance of life. During the earliest periods, Earth's crust had been largely oceanic, dense, dark, basaltic rock that recycled easily into the mantle. But as the planet cooled, lighter, silica-rich rocks began to form. These rocks were more buoyant and less likely to sink back into the mantle, giving rise to the first continental crust. The beginnings of small, scattered land masses emerged, floating above the denser oceanic crust. Over millions of years, these protocontinents grew, collided, and merged through the movement of tectonic plates, forming the first stable cores of continents, known as cratons. Many of these ancient cratons, some over 3 billion years old, still exist today at the heart of modern continents, silent witnesses to Earth's deep past. The emergence of continents transformed Earth's surface in profound ways. Land provided new environments for weathering, erosion, and sedimentation. Rivers carried minerals into the seas, enriching the oceans with nutrients. The chemical cycles of carbon, nitrogen, and other elements became more complex, regulated by interactions between land, sea, and atmosphere. Continents also altered global circulation patterns, influencing climate and ocean currents. The planet was evolving into a more dynamic, interconnected system, where geology, atmosphere, and hydrosphere worked together to maintain balance. As the continents grew and stabilized, Earth's climate system also matured. The carbon cycle, driven by weathering of rocks on land and sedimentation in oceans, acted as a natural thermostat. When volcanic activity raised carbon dioxide levels, the greenhouse effect warmed the planet, accelerating weathering that eventually drew carbon dioxide out of the air and locked it into rocks. When levels fell too low, cooling slowed weathering, allowing volcanic emissions to build carbon dioxide back up. This feedback loop kept Earth's climate within ranges that allowed liquid water to persist, despite fluctuations in the sun's brightness. It was within this environment that the earliest signs of life began to appear. The exact origins remain one of the greatest mysteries of science, but evidence suggests that life emerged remarkably early in Earth's history, possibly as early as 3.8 to 3.5 billion years ago. Microscopic fossils, isotopic signatures, and ancient microbial mats, known as stromatolites, reveal that tiny organisms were already inhabiting the seas. These were not plants or animals but single-celled microbes, simple in structure, but extraordinary in their adaptability. The origins of life were likely tied to Earth's unique chemistry and geology. One leading idea is that life began in the deep oceans, near hydrothermal vents. Here, hot, mineral-rich water gushed from the seafloor, creating chemical gradients that could power the synthesis of organic molecules. The vent environments provided energy, protection from harsh surface conditions, and abundant raw materials. Another possibility is that life began in shallow pools on the surface, where cycles of drying and wetting concentrated organic molecules, allowing them to form increasingly complex structures. Perhaps life's ingredients were also supplemented by molecules delivered from space, carried by comets and meteorites that bombarded the early Earth. Regardless of the precise origin, once life appeared, it began to alter the planet itself. Early microbes metabolized chemicals from their environment, releasing byproducts that changed the chemistry of the oceans and atmosphere. Some of the earliest life forms used processes such as fermentation and chemosynthesis to extract energy from their surroundings. Later, a group of microbes evolved the ability to harness sunlight through photosynthesis. This innovation, which may have first appeared around 3 billion years ago, was revolutionary. Photosynthesis used carbon dioxide and water to produce energy, releasing oxygen as a byproduct. At first, oxygen levels remained low, absorbed by iron and other elements in the oceans. The reaction of oxygen with dissolved iron produced vast deposits of banded iron formations, layered rocks that record this chemical revolution. Over time, however, oxygen began to accumulate in the atmosphere, leading to what scientists call the Great Oxidation Event around 2.4 billion years ago. This transformation would ultimately make Earth's air breathable for complex organisms, but in the beginning, it was a crisis for many anaerobic microbes, which found oxygen toxic. Yet from this upheaval came new opportunities. Oxygen allowed far more efficient energy production, laying the foundation for the evolution of more complex life. The interplay between geology, chemistry, and biology was now unmistakable. Life was no longer just a passenger on Earth. It had become a powerful force shaping the planet's environment. Microbes altered the atmosphere, stabilized sediments, and influenced nutrient cycles. The rise of photosynthetic organisms cooled the planet by removing carbon dioxide, sometimes plunging Earth into icy episodes known as snowball Earths, when glaciers may have covered the entire planet. Each cycle of change pushed life and environment to adapt, driving evolution forward. Meanwhile, the continents continued their slow dance across the globe. Through the process of plate tectonics, they drifted, collided, and broke apart, forming mountain ranges, rift valleys, and supercontinents. One of the earliest known supercontinents, Kennerland, may have assembled around 2.7 billion years ago, only to break apart later. These tectonic cycles enriched the biosphere, recycling nutrients and creating new habitats. They also ensured that Earth's surface remained active, unlike Mars, which froze geologically, or Venus, where stagnant crust led to a catastrophic resurfacing. By the close of these early chapters, Earth had transformed from a molten, chaotic world into a vibrant planet with oceans, continents, atmosphere, and life. The processes of stabilization, continental growth, and biological emergence were not separate threads, but part of a single tapestry. Continents enriched oceans, oceans regulated climate, and microbes altered the atmosphere. Each system fed into the others, creating a self-sustaining cycle that endured across billions of years. It is astonishing to consider how much had already been accomplished by this time. In less than 2 billion years, Earth had gone from cosmic dust to a planet with living organisms that were actively reshaping their world. The stage was now set for the long evolutionary story to unfold: the rise of eukaryotic cells, the explosion of multicellular life, and ultimately, the appearance of animals, plants, and humans. But all of this was possible only because of the groundwork laid during these earliest ages: the stabilization of the environment, the growth of continents, and the dawn of life. In reflecting on this history, one truth becomes clear. Earth is not merely a backdrop for life, but a partner in its story. From the swirling nebula that gave birth to the planet, to the magma oceans that cooled into continents, to the microbes that breathed life into the atmosphere, every stage has been a dialogue between planet and organism, matter and energy, chaos and order. The Earth is both the stage and the actor, both the canvas and the brush. Today, when we gaze upon our planet from space, a shimmering blue orb suspended in darkness, we are seeing the product of this extraordinary journey. The continents that rise above the seas, the air we breathe, the oceans that cover the globe, and the life that thrives in every corner are all outcomes of processes set in motion billions of years ago. Earth is a living archive of cosmic history, a reminder that from fire and chaos can emerge stability and beauty. The story of Earth's formation is not just the story of rocks and gases, impacts and cooling. It is the story of transformation, resilience, and interconnectedness. It shows us that even in the harshest conditions, creation can emerge, that destruction and renewal are part of the same cycle, and that life is inseparable from the planet that cradles it. In understanding how Earth was formed, we are not just studying the past. We are learning why we exist at all, and why our world is such a rare and precious oasis in the vastness of the universe.